Hello,
Hello.
how are you? How's it going?
Uh, Good.
That's good.
And
That's good.
I don't know. I got finals next week.
Finals already? Wait, next week? Finals?
Yeah.
What? Wait. Wait, so after the finals, you have a week break or 2 week break, 3 week break, or is it midterms?
No, it's just right after. You go back to school again since there's no holiday.
Oh, okay. So are you studying in new set of classes after the finals next week?
It's the same.
Or
It's a semester, so this
yeah,
all my classes are the same next quarter.
I see. Okay. Um, thing. See. Hello, Camilla. Hello, Elysia.
Hi.
Hi. Let me go share my screen. Here you go. See. Okay. Yeah. So, did Farhat go over the carboxylic acid nomenclature in class today? Because I think different professors like emphasize different things in nomenclature, so I want to make sure like I go over the stuff that he goes over too, you know. Because I know what Levin's helix and Nussiri wants for nomenclature, but I want to make sure that I know what Farhat wants too. Did he go over that in class today?
He honestly just gave us a slide of like the derivatives and said just memorize these, but he didn't go over any of the rules for any of the acids or yeah.
Oh, like any of the nomenclature rules. He just gave you like a list of the things and it said to know it already, and he moved on to the
Yeah.
next.
And then he
Oh,
moved on. So
yeah. Did he provide any practice problems exams?
he has homework, but I have not opened it yet.
I see. Okay. So we're gonna go over Levin's helix and the series nomenclature, and I think that should be the same as Perhas as well. Um, so the carboxylic acid derivatives are going to be like what we said yesterday, which are the carboxylic acids. So let me just write that down again. The parent function is, let me put the examples down here. Um, Carboxylic acid, and then the derivatives are going to differ by this variable group right there, right? If you have a halogen right there, that's going to be an acyl halide. If you have another carboxylic acid looking kind of thing, that's going to be an anhydride. If you have an OR group, that's going to be an ester. And then if you have some kind of amine group, it could be primary, secondary, tertiary amine, giving you different types of amides. Um, those are the four main carboxylic acid derivatives. A cousin of this family is going to be the nitrile, the uh, CN, where there's a triple bond between the carbon and nitrogen. Right. This is a cousin of these derivatives, and we'll figure out why as we go on to the reactions of that. But um, carboxylic acids will have priority over other carboxylic acid derivatives, with the others following in order of reactivity. So acyl halide would be number one, anhydride, ester, amide, and nitrile. So basically, what I put in this form right here, right? Carboxylic acid is going to be the parent function, so that's the highest one out of all of these, and then it's going to be the acyl halide, where the word acyl, when you think of that, think of carbonyl, carbon double bond oxygen. The acyl group is going to be this carbon double bond oxygen right there. This is going to be, you could see as acyl anhydride, or you might just see as anhydride. The more common way to see it is just anhydride. Um, you could see an ester, you could see an amide, and then this is a cousin, nitrile. Okay. Um, Now, if the carbonyl or acyl group is a carboxylic acid, you drop the E ending of the suffix name and then add oic acid. If it's an acyl halide, you drop the E ending and add oil halide. We'll see examples of these. if you have an ester, which we did yesterday, you drop the E and then you add O8, right? But that's one of it. The other part of the ester is that the OR group of the ester it has its own first word, right? Remember that from yesterday? Like, let's say I have something like this. Say, oh shoot. Oh yeah, try this practice nomenclature problem as practice, because yesterday I said we were gonna go back to like a problem on the practice exam after I go over the ester examples, which I didn't. So this is gonna be very similar to that problem on the exam. Well, first, do you know what's the highest priority functional group in this whole structure? Let's start with that. What's the highest priority functional group in this molecule?
The ester?
Yep, the ester. So um, this is going to be our number 1 atom, number 2, number 3, number 4, number 5, number 6. Since the ester is our highest priority group, these alcohols here are going to be our substituents. Do you remember the word we use if alcohols are our substituents?
Hydroxy.
Hydroxy. That's right. That's right. So we're gonna have 4, 5 dihydroxy. Right. And then since we have 6 carbon as our longest chain, that's gonna be hexane. We drop the E and add O8. What's the first word of this ester going to be?
Propyl?
Yeah, propyl, because the OR group is 3 carbons long. So the first word is going to be propyl, and then everything else comes after that. And there's a space between the OR group and everything else, which is 4, 5 dihydroxy hexanoate.
So we always name the R group first.
Yeah, always name the R group of the OR group first, and then everything else afterwards for esters. Yeah.
Just for esters.
Yep, just for esters.
Okay.
Esters will be the only one that has 2 different words to it, like a space in between. Right. The other ones will be one word. Acyl will be one word, anhydride will be one word, amide will be one word, nitrile will be one word. But ester is going to be 2 words, where the first word is the R group of the OR group. Yeah. Okay. For amides, we drop the E and add an amide. For nitrile, put it nitrile. This is like figuring out the longest chain according to which numbers the substituents, what substituents are attached to which carbon. This is talking about the ester. The OR group of esters is named separately, and the alkyl group is in front of the rest of the name, like methyl butanoate. For amides, the N alkyl group, the NR group for amides is named as a substituent. Instead of a number, we use the big capital N instead of a number, like NN dimethyl, and whatever the thing is for amide. Like we did on last night's office hours. We did some examples of that. We'll do some more examples here too. List of substituents in alphabetical order. Yep, this is the regular one. And in alphabetical order, we ignore that first word, first letter right there for di. So we don't consider D as an alphabetical order. We'll consider H, right? Yeah, it's just right here. Di, tri, tetra. Prefixes do not count towards alphabetical order unless they are part of a complex branch substituent, like isopropyl, tert-butyl, sec-butyl, those complex substituents. And then if there's any stereochemistry, R, S, E, or Z, that will be in front of the name in parentheses. Right? Okay. So let's do two examples here, and then move on to 118A question. Let's see. Okay. That one, and let's do this one. Okay. Try naming the ester here, and then walk me through your thought process. What do you look for first, and how would you name this ester here?
It starts with the R group, which is butyl,
Right?
and then there's a space, and then we count starting with the carbonyl carbon. There's 6, 7 dichloro, and then there's also 2 hydroxy.
6, 7
And
dichloro.
so, yeah, so chloro goes first, then
Yep.
hydroxy, and then octanoate.
Yep, octanoate, right? 2 hydroxy. Right. And what would the first word of the ester be?
Butyl.
Yep, butyl. Nice. Yeah, you got it. 2 hydroxy octanoate. That's it for the ester. And then we also have butyl as the first word. Yep, nice. Okay. So another thing for acyl halide is that, oh yeah, they said it right here. We drop the E ending and we add the oil halide. And the halide, don't put halide. It will be the halide that you have specifically. So if it's a bromine, then you say oil bromide. If it's a chlorine, you say oil chloride, right? So in this case right here, we have an acyl halide where there's a carbonyl here and a halogen attached to that carbonyl. It's specifically an acyl bromide. So that's going to be our number 1 atom, 2, 3, 4, 5. We see that we have an alkene right here. And do you know if this alkene is E or Z back in 118B?
Z.
Yep. Well, Z, yep. Yeah, that's right, that's right. Because if we look at this carbon right here, the higher priority group is going to be this group right here compared to the hydrogen. And if we look at this one right here, this is the high priority group of that carbon. We see the 2 highest priority groups are on the same side. That's going to be Z, right? Don't think about it in terms of size, like this. Like even though this might be bigger, this bromine has a higher atomic number, so that's why that's the highest group. So we're gonna put 2Z. We have 3 bromo, and then we don't say pentanoyl bromide because we have an alkane. Right, we have an alkene, so we have to put an ene in that name. Where the alkene starts at carbon 2. Right, so it's going to be 2 pentanoyl bromide, or you could have it like this. Like that. Okay. Either one would work. Any questions on this acyl halide right here?
So we just put the halogen at the end.
Yeah, we put the halogen at the end as a halide, ide, and there's a space there as well. So that's the iso halide actually has 2 words as well, like the ester.
Oh, okay.
Right. So that's the other one that has 2 words.
Thank you.
Right. Yeah, no problem. Yeah, and then I'll like try to compile more practice songs because I don't have that many for our session coming up this week too.
Thanks.
Yeah. Let's see. Let's move on to 118A. Elysia, do you have any questions so far? Oh, and hey, Andrea.
Hello.
Hi. Yeah. Do you have like a homework problems? Because I know Fahrenheit 118A has homework as well, and then we did some homework problems on last office hours. Does Wei also give homework or anything to do to practice for the week? I see. Okay. Let's see. Have you had discussion yet for 118A? Not for the first course, I see. What did you guys learn so far? What topics? Did you guys learn bond line, structure, Lewis structure, Kikuchi structure, resonance, hybridization, formal charges? Yeah, the mic doesn't work. Let's see. Um, okay. So let's okay, we can go back to 118C. Do you guys want to do more nomenclature practice problems, or do you guys have any like other practice problems that you guys want to work on?
Can we do a couple nomenclature? And then
Couple of
also, I was wondering if you knew, he's going over acidity.
uh-huh. Oh, acidity. Right.
Yeah.
I see. Yeah. Okay. Let me write down 2 more nomenclature problems for you to try, and then I'll go over a 118A thing, and then we'll go back to that nomenclature problem.
Thank you.
Yep. No, they just give us that.
Does my mic work now?
Yeah, we can hear you now.
Okay, thank you.
Yeah. Let's see. Let me give them 2 practice problems here. Let's do this one. Okay, this is going to be from Helix's practice midterm 1 in spring 2023. Right here. Okay. So I want you to draw the structure or the molecule. Draw the structure of 3 chloro. Oh, okay. This might be a little bit weird one, but we'll go back to this. 3 chloropropyl, 2 methyl butanoate. So draw that structure as the first one. Another one is going to be provide the IUPAC name. Provide the IUPAC name of this structure here. Okay. Yeah. take a screenshot. Okay. Let's see. Yeah, so what was the last thing you went over, Elysia? What topic?
It was just nomenclature. We didn't really go into naming stuff just yet.
Uh-huh.
But we did say that we may be behind just because she is new at the teaching part.
Yeah. Right. Let's see.
But I can catch up.
Uh-huh. Did she go over drawing bond line forms yet? Or
The calculate,
yeah.
the
Uh-huh.
different forms, yes.
Condensed formula.
Right, yeah.
Uh-huh. You did. Okay.
And I
Let's
think
do some
that was,
practice
the
songs.
last thing, and she also talked about resonance structure and drawing arrows to where they go.
Drawing arrows. Right. Like where the arrows go.
Yeah.
Stuff like that. Okay. So let's do converting a condensed formula into a bond line formula, and then a bond line formula to condensed formula, and then try one resonance problem, like draw the different resonance structures, and then predict the major contributor of that resonance set, and then we'll go back to checking these answers here. Okay,
Okay.
let's do that. Actually gonna give it like is this right here. This is gonna be the big one here. Actually, let me just screenshot this. This is way too big. A content review 1. Let's see. Okay, so we have this structure here. To convert this into bond line form, the carbons are going to be represented by a point, right? And then they're usually going to be in a zigzag formation to show the tetrahedral shape geometry, right? And then the hydrogens here are going to be invisible. And for carbons to be neutral, they want 4 bonds, right? We see that all of these carbons here are neutral because all of these carbons has 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Even this carbon right here, that's double bonded because a double bond counts as 2 bonds. 1, 2, 3, 4. Even these carbons here, these carbons are also has 4 bonds, which is why they are neutral, right? So when you see a big group like this, find the central atom, right? Which is going to be this carbon right here that I'm going to highlight in yellow. That's the central atom. So I'm going to draw that central atom as a point like that, right? Now, are you familiar with this? Like this stuff?
Yes.
Okay. Can you explain to me how would you convert this structure into bond line form?
Well, you want to start off seeing what it's or actually, can you clarify the question?
Yes. I want you to convert this whole structure into bond line form. And then from there, we'll move on to converting onto condensed formula.
Well, I know if it's connected to other carbons, then you want to include it, but typically not hydrogens.
Right.
And like you said, it's in a zigzag form.
Yeah.
So
The zigzag form.
um,
Right. So we see that this yellow carbon right here is that one right there. Let's focus on this one right here. to draw these two carbons, we could draw it like that,
Right.
right? And then we have two other groups coming off of that carbon, just like that. 1, 2. And then the way you draw it, like doesn't matter. You could draw it in that orientation or this orientation, or even like let's say like that orientation. But don't draw it like in a straight line. Like if you do it like this, don't draw the other carbon like that,
Oh, okay.
because that looks like one long single bond to
Right.
one carbon. Right? Make sure there's like a bend to it. Okay, so I'll draw it like this. Okay, and now we see two other carbons coming out of that central carbon, so we could draw those two other carbons like this. 1, 2, just like that. Right, and then the next carbon right here is attached to an alcohol, OH, which I'm gonna draw out as that OH alcohol right there. Right, and then this carbon right here is gonna be this carbon. The next carbon is going to be double bonded, which we could represent like that. Right. And then the next carbon is going to be right there, which is this carbon that is attached to a methyl group. So that's that methyl group right there. And then the next carbon right here is attached to a carbonyl, a carbon double bond oxygen, which is this carbon double bond oxygen like that. Right.
Right.
And then the next atom is not a carbon. It's an oxygen, so we have to draw and write an O right there to represent that oxygen atom, which is attached to a methyl group. Oh yeah, another thing for 118A at the beginning is that I think she gave you a list of functional groups to know and remember. Like Chem 2C, you know how you were learning about like the functional groups. What functional groups are present in this molecule, or have you memorized the functional groups yet? It's okay if you haven't memorized it yet.
I did memorize them, but I'm a bit rusty on them now.
Right.
From 2C. Let me see if I can recognize any.
Yeah.
Well, functional groups. I mean, I see the alcohol. I see a carbonyl, or the one between
this one right here.
Well, that one's an alkene.
Alkene, right? Alkene. And then this is a carbonyl, like you said.
Yeah, carbonyl. But it's a specific one, right?
Yeah, that's a specific one, because like carbonyl is a big umbrella term for a lot of things. Like ketone, aldehyde, carboxylic acid, ester, amide, acyl anhydride, acyl halide. So we have to be more specific.
Yeah, I get confused with the
carbonyl
ketone and yeah.
Right. This whole thing right here, when you see carbonyl next to an OR group, like that, right? That is an ester. A lot of people confuse that with ether. Do you know what an ether looks like?
Yeah, it's like you did the ether or, so it's like one or R or R.
Yep, R O R or R prime. Some examples would be like that, or even like that. Yeah, those are ethers, not esters. It would be an ester if there's you add a carbonyl. Like if you add a carbonyl here, now there would be esters. But no carbonyls, that's just an ether.
Okay, yeah, because that's part of the its own group.
Yeah, it's own group right here. Like if you ignored this carbonyl here, right, then this would be considered an ether.
Ether, yeah.
Right. But because the carbonyl is right there, we call that an ester.
Right, because it's a carbonyl group.
Right, because it's a carbonyl group.
Okay.
Do you know, let's say, what this functional group is?
Is it a amide?
So yeah, close.
Amine,
okay. Right. Now, what if I put that carbonyl right there?
Amide.
Yep, amide.
Okay.
So that's like very similar to what we did. This is an ether, this is an ester because of the carbonyl.
Right.
This is an amine, like without the carbonyl. And then the amide is the carbonyl with that amine next to it.
Right. Okay.
And then you'll learn all about this, like chemistry of it, in 118C. But you have to recognize what the functional group is in 118A, because she will ask like what functional groups are present, and then you'll see these right here, like amide, amine, and stuff like that. Recognize it, right?
Okay.
Uh-huh.
So the
Okay.
majority of it, like as for now, is just like review-ish. Would you say there's anything like new that probably was not introduced?
Right now in 118A, you probably learned all this in Chem 2C already, like bond line form, Kikuli structure, condensed formula, hybridization, formal charges, resonance. You'll start getting into like the organic chemistry reaction when you learn about free radical halogenation. That's when you learn about your very first reaction and mechanism. Yeah, so right now it's all reveal basically from Chem 2
Okay.
series, right?
Do you know like what week is mechanisms introduced?
What week mechanisms and reactions? They're usually different professors have different paces. Levens has like bi-weekly quizzes. Nasiri has midterms. So Levens would go. I would say she's a little bit faster than Nasiri. Probably by it's gonna be on the first midterm. Oh, for Nasiri first. So by week 2 or 3. So after the first week, you'll get into the reaction. So probably next week or week 3, you'll learn your first reaction and mechanism.
Okay,
Right?
thank
Because you
you.
still have to go over resonance, the major contributor factors. What else is there? Let me check my content review notes here. Okay, that's content review 1. Content review 2. Yeah. Like, how are you feeling about OChem so far? Like, is it doable right now for you?
I think it is, but it gets me a little bit scared that I'm like probably not studying as much as I should, or like if there's something I'm just missing out because there's discussions that's considered a lecture as well.
Yeah, right. Resonance nomenclature. Nomenclature. You did do some of that in Chem 2C, right?
Yes.
Yeah. That's a little bit reveal, but OChem goes a little bit more in detail.
I think what I get a little bit confused on is where is it?
Have
Like
you learned about?
what is a major or minor contributor?
Oh, major minor contributor. Right. For resonance structures, I think we that
Yes.
here as well. Let me increase this. So these are the factors that you have to know when determining what's the major resonance structure. So let's do one example
Okay.
of that. Wait, actually, let me double check with the one when you can see nomenclature and teach them do go over practice song, and then we'll go out to resonance after that.
Okay.
Right. Okay. Camilla and Andrea, have you guys gotten these problems down for the nomenclature?
Yeah.
How did you draw the first one? The 3-chloropurple is probably the trickiest one here.
Um, we did the ester with an R group of 4 with a chlorine attached at the end. And then we did a butyl with a methyl on the second one next to the carbonyl.
Did you get this as the OR group right here?
Yes.
Yes. Yeah, that's probably the trickiest part. This is the 3-chloropropyl. And then the other one was this one right here that you guys got.
Yes.
Nice. Okay. So now have you guys gotten the IUPAC name for the second one?
Yeah, we did 2-ethyl,
Yeah.
4-hydroxy pentanoyl space chloride.
Yeah, nice. You guys got it. Not that bad, right? Like once you get the system down, the rules down of the nomenclature, it's just a lot of like practice. It's like pretty straightforward once you have the rules down. for nomenclature. Right. Okay. Oh yeah, you wanted to go over acid-base stuff, or wanting to see acid-base stuff?
Oh yeah, he went over acidity and basicity. I don't know if I'm saying that right. Today in lecture.
Acidity and basicity. Let's see, how can we do this? Acidity and basicity. Let's see. Oh, can you post your lecture notes to the Google Drive, and then I'll check it, so then I know specifically like what he's going over, so I can like come up with some something to um
Oh
go
yeah. The
over
only thing is that he
Uh-huh.
doesn't post. He only posts the slides without the details. Like
Oh, post the slides.
it's like fill in the blanks.
Yeah, I see, I see.
But I take photos, so I'll post
Uh-huh.
the photos.
Okay. Yeah, thank you, thank you. Let's see. Yeah. Acidity and basicity. Right. Carboxylic acids, they're gonna be very basic. I mean acidic. Acidic. This hydrogen here is very acidic. Right. And the reason why is because when we introduce some kind of base to it, like let's say hydroxide ion, that base is going to deprotonate the carboxylic acid by grabbing this hydrogen. And then this bond between the oxygen and hydrogen here is going to go onto the oxygen, giving us this conjugate base right here. And it is conjugate acid, right? Where this conjugate base is stable because it can do resonance, right? And then if this is a more stable conjugate base, it's a weaker conjugate base because it's already stable, happy on its own, doesn't want to react. And if it's a weak conjugate base, that means that this is a strong acid. Well, I think what he was going over in lecture now, he was comparing the acidity between the derivatives, right? The acidity between an acyl halide, anhydride, ester amide, which one's more acidic and why? Let me check. Let's see. No, past resource lecture notes.
I don't know. I think he's not going in order because I don't think we've done the derivatives yet.
Oh, so acidity and basicity. That's very general. Like acidity and basicity of carboxylic acids, of like in general.
Oh, okay, then maybe he has. My bad.
Oh yeah, I'll check the thing and then we'll see. See, is it uploading right now?
Sorry, 1 second.
Okay. Wait, let me actually pull up the resonance. Right here. Wait, Elisa, you're familiar with calculating the formal charge of atoms, right? Like, and the non-bonding electrons it has, like if it have a negative charge, positive charge.
Yes, I'm familiar with that.
Okay. Let's get. And then resonance. I think you know the arrows as well, like where they move.
Yeah, there was like a part where Wei was talking about the 4 rules where like structure with maximum octets are important. Negative charge should be located on the more electronegative atom. Structures with less separation on opposite charges are more important. Resonance contributors. I think I get it, but I guess like drawing the arrows is just a little bit confusing to me.
Oh yeah, the arrows, like where they go and stuff like that. Like how do you know when to stop in resin structures? Because there's a whole bunch of resin structures. There's a lot of minor, super minor ones. Lehman's makes it very clear on how many she wants because she provides boxes for the resin structures.
Yeah, I think it's like the minor and major that kind of confuses me.
Yeah, let's do some practice ones on that. See here. Let's do. I have a lot here. Okay. Yeah. Let's go see the notes. The one you can see. Oh, I see. Chapter 19. Yeah. And I also have a Kahoot on resonance. So maybe we could try that at the end of the office hours if you guys are down. Let's see. Here's application. Oh, dot noteful. Wait, can I open it through here?
I'm uploading it as a PDF.
Oh, okay. Because yeah, it was telling me to open it in some platform or application, but I was like, I don't know what to open it with. Oh, I see. Okay, right here. Send a copy. Notability. Downloading. Okay. And do not import open. Okay. Okay. The functional behavior of carboxylic acids can be anticipated if the carbonyl alcohol, the hydroxygen is acidic because it leads to a stable conjugate base. When we rip off the hydrogen from this oxygen right here, giving this oxygen a pair of electrons from this bond, that oxygen will gain a formal charge of -1 because now it has 3 lone pairs of electrons, where this negative charge is delocalized. It could move around. Think of it as like having more space. Like if we compare this oxygen minus versus this oxygen minus right here, think of the electrons as horses, right? And then think of delocalization as a big field for the horses to run around, roam around, and be more stable, more happy, right? And think of this right here as being localized in one small room, right? Not a lot of space to roam around, not a lot of space to run around. So the horses here are gonna be less happy, less stable. Whereas if the horses or electrons can move, be delocalized, then that's gonna become more stable. right? Resonance. Like that. This is localized, this is delocalized. And then the more stable the conjugate base is, the weaker the conjugate base it is, meaning that it came from a strong acid, right? So that's what that concept is talking about here. And the oxygens are basic and nucleophilic, and the carbonyl carbon is subject to nucleophilic attack, right? So you'll see in upcoming reactions and mechanisms this common pattern where the carbonyl oxygen of the carboxylic acid or derivative is going to be the nucleophile or acid or base, right? It's going to attack some kind of electrophile or some kind of acid, right? This carbonyl oxygen right here. Some people might say, like, ask why not this oxygen right here? And then we'll explain that through resonance again. Okay, resonance will like show up again and again and again, like all throughout OChem. So let's see what happens when we protonate the carbonyl oxygen versus the alcohol of the carboxylic acid. Right. Okay. So if we have some acid, strong acid like H2SO4, we could protonate the carbonyl oxygen, giving us this conjugate acid. Or we can protonate the oxygen of the alcohol, giving us this conjugate acid here. Which conjugate acid do you think is more stable and why? Would it be this conjugate acid or would it be this conjugate acid?
I'm not sure.
That's okay, that's okay. So if we compare the charges of the structures here, right? We have a positive charge on both structures, positive charge on this oxygen and positive charge on this oxygen. So we can think about the electronegativity factor, right? Because these oxygens are the same atoms. They have the same electronegativity. We can't think about that factor. The next factor we have to look at is resonance. Which one will have more resonant structures, right? We see that this structure here can do resonance by moving a pair of electrons down to make a double bond there, popping this double bond onto that oxygen right there, giving us this resonance structure here. Right? Where the positive charge shift from this oxygen atom to this oxygen atom. So we conserved the charge, the formal charge of the resonance structures, which is good, right? Whereas this one here has no resonance structures at all, right? We can't make a triple bond here. That's going to be bad. We can't do that. Okay. We can't also do this because this is going to be very unstable. Like if we try to shift that double bond down to make a double bond there, that's going to give this oxygen here 1, 2, 3, 4, 5 a positive charge, and then this oxygen here 1, 2, 3, 4 a positive 2 charge. This is extremely unstable, extremely unlikely to exist. But that's why this conjugate acid here is more stable, right? More stable conjugate acid. This is a less stable conjugate acid. And if a conjugate acid is more stable, would it be weaker or stronger?
A weaker, it's the opposite, right?
It's the opposite, right? Because it's more stable, more happy, weaker conjugate acid, meaning that it came from a strong base. which the strong base is going to be this carbonyl oxygen right here, right? Relatively strong base. This is a stronger base than this oxygen here. This is a weaker base. Weaker base, because this is a less stable conjugate acid, making this a stronger conjugate acid. So that's why when you see carboxylic acids, here's the thing to know about this. We call them amphoteric, where they could act as either an acid or a base. The acidic portion of the carboxylic acid is that hydrogen of the OH right there. The basic portion of the carboxylic acid is the carbonyl oxygen right there. Carbonyl oxygen, not the oxygen of the alcohol, but the oxygen of the carbonyl. That's the basic portion, because it leads to the more stable resonance structures, right? If you protonate or attack something with this right here, it gives the more stable conjugate acid or like resulting thing. If you deprotonate this hydrogen right here, it will give a stable conjugate base because it could do resonance. So everything would like fall back to resonance. More resonance, more stable. Right? Okay. Yep. Over here, yeah.
Sorry, will the carbonyl, the oxygen, always be basic, or is that just in this scenario?
Yeah, the carbonyl of the oxygen will always be basic. If you put a strong acid like H2SO4 or H3O plus in the solution, the carbonyl oxygen here will always get protonated. Always get protonated, right? And that's going to be the first step of a lot of reactions you see in this chapter. There's going to be a lot of reactions in this chapter, but don't get overwhelmed because they follow the same pattern, right? And then the pattern's first step is usually protonating this carbonyl oxygen right here. That's usually the first step, right? And I'll go over the other thing that he went over for that. What is the partial charge of this carbonyl carbon right here?
Positive?
Yep, partial positive, making it electrophilic, right? Not nucleophilic. So the carbonyl oxygen is going to be the base, the basic component, or the nucleophilic component. Right? But usually in the mechanisms, you see it as a base getting protonated, right? Oh, wait. Yeah, I think you guys do know this concept already, because this is in 118B when we went over ketones and aldehydes. What happens when I introduce a strong acid here? What do you think will happen first?
It takes the H of the acid,
What atom takes the H? Would it be
the oxygen of the
Yes.
carbonyl?
Of the carbonyl, right? Oxygen of the carbonyl takes the H of the acid, kicking out that to create HSO4 minus, which
Yeah.
would give us this conjugate acid right here. What happens to the partial charge of this carbonyl carbon? Like, does it get smaller or bigger? Do we activate or deactivate the electrophile?
I don't remember.
Oh, yeah, it's okay. It's okay. So when we protonate the oxygen, right? This oxygen with a positive charge is now unstable, right? So it wants to basically pull on the electrons more strongly to become neutralized again, right? Making this carbonyl carbon a bigger partial positive charge. So you can think of this as activating the electrophile, where weak nucleophiles can then come in and attack that strong electrophile. Because you could consider this as a weak electrophile, and then you could consider this as a strong electrophile. Does that sound familiar?
Wait, sorry, can you explain why it's a bigger
Mhm.
partial positive?
Yep, it's a bigger partial positive charge because if I have a positively charged oxygen like this positively charged oxygen wants to take that bond to give this resonance structure here, right, to become neutral. But when that happens, we have a full positive charge on the carbon right there, right? We could also do that in the first carboxylic acid that is not protonated yet, like this. Right? But this oxygen right here is not as hungry for electrons as this oxygen is. This oxygen is more hungry for electrons because it has the full positive charge. So it's going to pull on the electrons more. And then if it's pulling on the electrons more, it's making this carbon more positively charged. Whereas this oxygen is not pulling as hard, making this carbon not as positive charge. It has its electrons still. Right. Whereas this carbon here on the other side is losing more electrons, becoming less negative or more positive.
Okay.
Right. So yeah, 3 things here for carboxylic acids. This is the acidic portion. This is the basic or nucleophilic portion. And this is the electrophilic portion of carboxylic acids. Right. So these are the properties of carboxylic acids and how they react in mechanisms. If you introduce a base to the solution, that base would deprotonate the carboxylic acid by grabbing this acid here. If you put an acid in the solution, this carbonyl oxygen would grab the H from the acid. If you put some kind of strong nucleophile, a hard nucleophile, like a Grignard reagent or a reducing agent, it would attack this weak electrophile, right? But if you convert it into a strong electrophile by activating it, protonating this carbonyl oxygen, weak nucleophiles like water, alcohol can attack that strong electrophile. So this is going to be an overview of all the reactions that we're going to learn about carboxylic acids here. But before he goes over that, he's going over like the properties of this carboxylic acid, like what part serves as what in the reaction, right? Like this carbonyl oxygen serves as a base or nucleophile in the reaction. This hydrogen of the OH serves as an acid. This carbonyl carbon serves as an electrophile in the reactions that we're about to learn in the carboxylic acid chapter.
Okay.
Yeah. Okay. So let's do some field 118A resonance structures and determine the major resonance contributor. Right. Okay, let's do that. Yeah. Okay. Let's do this one. Let's do this one. Let's do this one. Oh, yeah. One more, last one. This one. Okay. So some tips for resonance is that the charge will be conserved for all resonance structures, the net charge. If you have a neutral structure that can do resonance, all the resonance structures would have to add up to 0, a net charge of 0. So if you have a positive charge, you have to make sure there's a negative charge that cancels that positive charge out. When you draw resonance structures, the thing that moves, like on the arrow, are the negative charges, the electrons. So you start from the electrons and then you move towards a void. You move towards something that's missing electrons, like positive charge. Negative charge goes to positive charge, not the other way around, right? The negative charges attack the positive charge. So that's what I think about when I do resonance structures. So let's look at this one here. I didn't give you the non-bonding electrons because they're going to expect you to know how many non-bonding electrons are there if they give you a formal charge, right? So if this carbon here has 2 hydrogens, a pair of electrons, how many non-bonding electrons would we have? Or how many pairs of electrons would we have in this carbon?
How many lone pairs?
Yeah, how many lone pairs of electrons?
1.
Yeah, one, right. So now, how would you draw the resonance arrows for this resonance structure? Where would you start your arrow?
Well, it needs. Well, are we assuming that if there's 2 hydrogens and then attached to the carbon, that there would be lone pairs attached to the carbon, or
Yes, the reason why I said that is because this carbon with the negative charge right here will have a negative charge because it has 1, 2, 3, 4, 5 electrons to itself,
Okay.
right? And carbon has 4 valence electrons because it's on group 4 of the periodic table. 4 minus 5 is -1, right? So now we can ignore the hydrogens. I just put the hydrogens there so then yeah, you don't get confused on like what's the invisible bonds there, right?
Okay.
Yeah, because usually if this is neutral, how many hydrogens would be on that carbon if this carbon is
3.
neutral? 3, right? But because that was negatively charged, it only had 2 and a pair of electrons, right? But if it was positively charged, then it would have how many pairs of electrons if it's positive?
Is it 3?
It would have 3 bonds
Okay.
like this, 1, 2, 3. So that means that it would have 3 electrons to itself,
Right.
right? But it would have 0 non-bonding electrons, 0 pairs of electrons.
Oh, okay.
When you see a positive charge, think of missing electrons, like missing a negative charge. So there's an empty p orbital there.
Okay.
But if we have a negative charge, that p orbital is fulfilled by this pair of electrons right there. Right? And
Okay.
in resonance, we move negative charges. We move the pairs of electrons. So where can we move? Like, let's say I start my arrow here. Where do we? Oh, wait. Where do we want to move this pair of electrons right here?
To the next bond.
Yep, to create a double bond right here. But that creates a problem because how many invisible hydrogens are attached to this carbon right here?
1.
Yep, 1, like that, right? So if we try to create a double bond right here, that's a problem because this carbon will have 5 bonds. 1, 2, 3, 4, 5. That breaks the octet rule. So to conserve the octet rule, we have to move this double bond somewhere. There's no other double bond, so I'm gonna move this double bond to this carbon right here. How many electrons are in this bond? How many electrons are in a bond?
2.
2, right? So I'm moving 2 electrons to that carbon, giving me this resonance structure there.
Oh, okay.
Right. In this case, they're basically identical, so there's no major or minor resonance structure here. But let's move on to the next one. This is a little bit different because now we're not going to move a pair of electrons. We're going to move something else. Right. You see this positive charge right here? That positive charge, think of that as the void. We want to go towards the void. So we want to
because you have to add electrons that way because it needs more.
Yep, we want to add electrons or give it electrons. So how can we give this carbon more electrons? What can we move to satisfy or fulfill that thing? Right. What's inside this thing right here?
2 electrons.
2 electrons, right? Those 2 electrons are going to go towards to make a double bond right there, creating this resonance structure here, right? But now this carbon right here lost a bond, giving it a full positive charge like that, right? Because before it had 4 bonds, now it only has
2
bonds that we could see, but there's one invisible one to the hydrogen, right? Which is why this has a positive charge. Because when we calculate the formal charge, it's going to be 4 minus how many electrons it has to itself, which is 3. 4 minus 3, positive 1 charge, right?
Yeah.
And then the other thing that we could do is move that double bond over there to do the same thing, to create a double bond there. Where would the positive charge be at now? Because we want to conserve the overall net charge of this structure.
Would it be on the left?
Yep,
Carbon?
on the left carbon, the leftmost carbon, because it lost a bond, right? So these are the 3 major resonance structures that you want to draw on the exam, right? There's a lot more though, but those are very minor. And then I'll show you the other ones that are also possible but are not like feasible, right?
Could you explain what you mean by minor, at least for that case?
Yes. In this case right here, like you said, we want to reduce the amount of formal charges in the structure, right? Like the resonance structure with the less formal charges, minimal formal charges, is more stable. The resonance structure with more formal charges is less stable. Like for example, if we compare this resonance structure to this resonance structure right here, this resonance structure is more stable, major, because there's 0 formal charges.
Oh, okay.
Right? Whereas this resonance structure here has 2 formal charges, 1 negative charge, 1 positive charge. If you see any kind of charge there, that decreases the stability all the time. Right.
Okay.
Now, I'm going to draw the very unstable minor ones, and I'll show you why. You'll see why. Right. And you could also do this. So what I did was I moved the electrons in the bond to the atom instead of making another double bond. You could do that, right? But that would be very unstable because we created 3 formal charges here, 1, 2, 3, 4, 5 formal charges there. If you see like a lot of formal charges like that, I think of very unstable, very unstable.
And that would be
very
considered
minor.
Okay.
Yeah, minor.
So if anything is considered major, that's like ones with like 0 formal charge?
0 formal charge, or the like smallest amount of formal charges, right?
Okay.
It could be 1 formal charge, because if you're comparing 1 to 3 formal charges, the 1 would win. Like the smaller number of formal charges would win.
Sense.
Because not all resonance structures will have 0 formal charges. Some resonance structures will
But
have
if you're
1.
doing a comparison.
Yeah, right. Between the comparison, and then once you draw resonance structures from there, you could increase it to 3, where the one with the 1 resonance structure will be more major.
Okay.
Right. Another thing for positive charge, carbocation, is going to be hyperconjugation. But we'll go back to that later on when we learn about reactions. But there's another factor, because there's actually a major resonance structure out of these 3 right here. right? And then I'll just show you the trick right now. Look at the positive charge. Which positive charge is more substituted? Which positive charge is more crowded, has more groups around it?
Is it the far left?
Right, so if we look at the far left right here, the positive charge is on this one carbon right here. How many other carbons is this carbon attached to?
Oh, it's just one.
One, so that's, we call that primary. Let's look at the middle one. How many other carbons is that carbon attached to?
2 other ones.
Yeah, secondary. This one is also primary. So the one in the middle, it's the most substituted because it's attached to 2 other carbons. That would make it more stable. And then this is due to something called hyperconjugation. You can think of it as because the positive charge is lonely, it has less electrons. It wants more friends to support it, right? It has more groups around it. It has more friends to support. It has a bigger support system, making it more stable, more major.
Okay.
Right, and you'll go back to this in the later upcoming weeks, right? Okay. So notice how we did it one at a time. We could also do it like all at once. Like we could just move that there, move this here, to get straight to this resonance structure here, right? Like in the difference between this resonance set and this resonance set is that the first one here, I did it one at a time. The second one here, I did it all at once, right? On exams, at the beginning stages of OChem, you want to go do the first route, like one at a time, because they want to test you on your resonance knowledge on like how the electrons are moving. But after you get past the resonance test, then you could save time by going straight from the first resonance structure here to that third resonance structure right there, right? Once you do reactions and mechanisms like that. Does that make sense so far?
Yes.
Right, but right now we want to do it one at a time like this.
Right.
Okay. Now, let's look at this right here. How would you draw the resonance structures of this? There's 2 more resonance structures right here that I want you to draw. How would you draw the first one, the first other one for this one? You might be thinking of the fast shortcut way, but I want you to do the 1 by 1 way.
Right. So would I just want to move the bond, like bond to the next bond, or is there like a thought process to moving them?
Yeah. So you see bonds here. So you usually see like you want to move it, but do you see a negative charge somewhere?
There is.
Yeah, it could be on a heteroatom, an atom that's not a carbon. It could be on an oxygen as well.
Oh, okay.
Like the negative charge
oxygen then. Yeah.
on this oxygen right here, right? Whenever you see a negative charge, right, I always look at that and I always move that for resonance structures.
Oh,
right?
okay. So that's okay.
So if I move this negative charge down to make a double bond right here, that's gonna cause a problem. Because what problem would it cause?
It would give the carbon to have 5 bonds.
Right. And how can we fix that problem? How can we conserve the octet role for that carbon?
Can you move it somewhere else?
Yeah, we can move this double bond here somewhere else, like that pair of electrons and that bond somewhere else.
Oh, okay.
Right.
So then, does that mean that we're focusing on the double bond first before we consider moving the
negative charge first? We consider the negative charge first, right?
Yeah.
Before we do anything else. The exception would be here where you have no negative charges, but you just have double bonds and positive charges. That's when you move the double bond towards the positive charge.
Okay.
Right. There's no pairs of electrons. There's no full negative charge here on this resonance structure. But when you do have a full negative charge, you look at the full negative charge first. Right. Where do you want to move this double bond right here? Where do you want to move those 2 electrons?
I would say can I move it to the one below it?
Oh, like a double bond right here?
Yeah.
You can do that, but that would also create a problem for this
Ooh, okay.
carbon. So when you do that, how would you conserve this is possible. Let's continue what you're saying. Like how can we conserve the octet rule for this carbon now? Where can we move this double bond?
To the one beside it to the right.
Right here.
Yes.
Right. So when we do resonance, right? Resonance is gonna
Oh,
happen between
okay.
sp2
Here.
orbitals. We cannot make a double bond right here because once we create 5 bonds there, there's nothing else to move. We can't move this hydrogen away. We can't move the hydrogen away. We can't move that single bond away. This is an sp3 roadblock. If you have an
Right.
sp3 roadblock, that's where you stop. You can't do any more resonance there. Like you stop there. sp3 roadblock. Right. Resonance is gonna happen between p orbitals, adjacent p orbitals. So most likely sp2 orbitals. So what we want to
Okay.
do is we want to move that pair of electrons onto that carbon right there, giving what charge to that carbon if we give it a pair of electrons. Right. Well, what charge would
Okay.
this carbon have here?
Oh, a minus.
Yep, minus charge, right? Because it has 1, 2, 3, 4, 5 bonds to itself. 5 electrons to itself. 4 minus 5, negative charge, right? Because it gained a pair of electrons, and the electrons are negatively charged. And this is good because notice how the overall net charge of the whole structure stays the same. Like we had a full net charge of -1. We still have a negative charge here in the whole structure. Right.
Oh, okay. So that's okay to give it like a lone pair because I was thinking like you need to move like a bond somewhere instead of like giving it lone pairs.
Yeah, it's okay to give it a lone pair. That's it might seem weird for to do that, but you could give a carbon a lone pair like that.
Okay.
Right? And that was a shortcut way. I wanted you to do the longer way, which is going to be on the exam, like this. So, thinking about what you just learned, right? How can we do the one by one way, where we can put a lone pair on an atom, on a carbon atom? Like if I move this negative charge to make a double bond there, instead of this double bond going to make a double bond here, where can this double bond go instead?
It can go directly onto the carbon.
Directly onto this carbon right here. Yeah, that would give this resonance structure right here. Does this make sense so far? With the negative charge on that carbon.
Yeah.
Right. And then how would you draw the next set of resonance structure? Next resonance structure from this point? What do you focus on when you have a negative charge?
We want to go towards like the positive.
Go towards the positive, or if there's no positive here, like there's no positive charge here, we have to start. What charge do we start with?
Neutral.
A negative charge. Negative charge.
Oh, negative. Sorry.
Right. We want to start with the negative charge, where from this point here, our negative charge is on this carbon right here. Right. So we're gonna move this negative charge down here to make a double bond, like that. And then move this double bond onto that carbon right there. Does that make sense so far on why I did that?
I think so, yeah.
Right. So that would give me this resonance structure right here. Right, which is the same resonance structure that we had at the beginning, right here, but we had to do one by one. We had to move this bond onto that carbon here first, and then make a double bond here to create that negative charge there later. This is probably the way that you're going to be tested at the beginning, right here, the one by one way.
We would have to do it one by one. We can't just
go straight through like that.
Yeah, so for the middle one that you just drew, it's okay to have like 2 arrows there? Or like
Okay. It's okay to have 2 arrows there, where if you move this pair of electrons to make a double bond right here, you would have to move this there because that would break the octet rule if you don't do that. Yeah.
Okay.
So those two arrows are showing the movement of two pairs of electrons. This pair of electrons and this bond right here. That's gonna become this pair of electrons right here. Right. Where this double bond right here came from that pair of electrons. This pair of electrons came from that bond right there.
Okay, so when we're moving lone pairs, like when do we know when to like stop, or like when do we know how many we can draw?
Yeah, we stop when once we have this one right here, look at the next atom. If it's an sp3 atom, you stop. That's an sp3 roadblock right there.
Oh, okay.
Right. Because resonance will happen between sp2 or sp atoms or p orbitals. Right. sp3 atoms has no p orbitals at all.
Okay, so you said sp2 and sp have?
sp2 has one p orbital. sp has two p orbitals. But
And
you
those
only
ones-
need at least one p orbital to do resonance.
Okay.
Right? So think of resonance as happening between adjacent p orbitals. That's the best way to think about resonance. Right? It's happening between adjacent p orbitals. And then we'll learn about hybridization later on, like how to tell if something is sp, sp2, sp3, p unhybridized or s unhybridized as well.
Okay.
That's actually important for resonance. Like I think you need to learn that before resonance. Like we need to practice that before resonance, right?
Right.
Okay. So what would be the major resonance structure from here? Where would the negative charge be the most stable at? What atom? What atom can hold the negative charge the best? The more or less electronegative atom?
One less.
So it's going to be the more electronegative atom because the electronegativity is like how strongly an atom can pull in electrons. So the atom that has a higher electronegativity wants to keep electrons. Like it can hold the electrons better. So what would be more electronegative, oxygen or carbon?
Oxygen.
Yep, oxygen, right. So the major resonance structure is going to be this first one right here.
Okay.
Right.
Because you said that oxygen is better at keeping its
Electrons.
Okay.
Yeah. Carbon is not because carbon is less electronegative. Electronegativity, you can think of it as how strongly an atom can pull in electrons or how well it can hold electrons. Yeah. Oxygen is more electronegative. It can hold electrons better than carbon, making this the major resonance structures and then the other ones minor because the negative charges are on the less electronegative atoms. Right. Which is this factor right here, the charge placement. We want the negative charge on the more electronegative atom. We want the positive charge on the less electronegative atom.
Okay.
Right. Negative charge on more electronegative atom. Positive charge on the less electronegative atom. Okay. Yeah. Any other questions, Elysia?
I think that's good for now.
That's good. That's good. Yeah. And then
Thank you.
yeah, no problem. For the future office hours, feel free to text me any problems you wanna go over, and then we could go over that in office hours as well. So then like we're like it could run more smoothly as well. But if not, we could just like free flow it on the spot too.
Okay, and then would it be helpful to just give you the notes that we have in lecture, or?
Yeah, that would be super helpful as well. If you could send that to me.
Thank you.
Yeah, no problem, Alicia.
Thank you.
Yeah. See ya. Good night.
See ya. Have a good night.
Hey, Ryan.
Hello.
Hey.
Are you busy?
I have to wake up at 6 a.m. tomorrow, and I'm planning to sleep at like 11 or 12. So, yeah, but I have some time.
Yeah, I've been experimenting with my sleep schedule because I have a lot of assignments to complete like last week and just like F me up. It F me up and now it's just like I'm kind of like going back to normal sleep schedule.
What's your normal sleep schedule now?
Right now it's just like around I mean last week it was like around 4 to 5, 3 to 4 hours, and then I just like cuz like I don't know what I was doing. It was just it was
4
not
hours of
working.
sleep usually?
That was just experimenting last week, just like, but I was way too tired and I couldn't listen in class, and I just fell asleep in my Spanish class first period, so that did not work. So
Yeah.
I'm trying to sleep earlier.
That's good. That's good. Um, you have
Hmm.
final exams next week?
It's more like midterms because you just go back to school right after.
Midterms. I see. Yeah, yeah. Midterms. I see. Okay, yeah. It's good. Yeah.
Hmm.
So if you were when you were experimenting 4 or 5 hours of sleep, like what time did you go sleep? What time did you wake up?
I want to sleep around like 3 p.m., 3 8 in the morning, and then I just woke up at like 7 ish.
Oh, I see. Wait,
But it
3
wasn't
a.m.
it wasn't consistent at all, and also
Uh-huh.
I felt like I didn't get a lot done during the day,
Uh-huh.
so I just started cutting, and I just started fixing it again.
Because you tried to get a lot done over the night, like night owl, but
Yeah.
that didn't work as well as like getting it done during the day for you.
Yep.
I see. Yeah, yeah. I feel um like for me, I don't know. It actually depends on the seasons of the the year as well, and like what I have coming up, like exams or something. But if there's no stress, I prefer doing like all the work in the morning, during the day. But if there's exams or finals coming up, then sometimes I like stay up pretty late to do the work.
I think like me staying up was like because that was just because I had like 3 tests all in one day.
3 tests on one day. Oh my god.
Yeah, and it just like messed me up like the whole week. It's
Shoot.
like
But
just after that, it's just like no, please.
yeah, yeah, like you don't want to do this again, huh?
Yeah.
But how did those 3 tests go for you?
Uh, it's like I don't. It's painful, honestly. It's just like I had to
Painful?
study for every single one, and then there was no time. So basically, I just got like literally my grade in every single class
Uh-huh.
is like C plus.
Uh-huh. Yeah, yeah. It's tough. Like you're in the like tough program, right? Like the one of the law science classes.
Yeah,
Yeah. And you're taking microbiome too, right? Like honors microbiome or something like that.
yeah.
Like advanced, like accelerated. Yeah, dang, that's tough too.
Mm-hmm.
And with AP Calc
No,
alongside with it.
with AP laying.
AP Lang, yeah. Like I'm taking microbiome this quarter too, so like maybe we could like study together sometime
Oh
for
dang! But
microbiome.
I mean, the thing is, it's like a flip classroom where you study at home and then in the classroom you do like labs.
Labs, yeah, I know. Like, is it all about like the bacteria, virus, fungi, um,
Mm,
parasites, or what is
protists,
protists, eukaryotes, prokaryotes,
archaea.
archaea? Yeah, dang.
This quarter, huh? Like after it ends, or
Yeah, yeah. This quarter, I just started this quarter, so I just started microbiome. So we could study for it. Yeah.
like 2 weeks ago, or just last week.
This week actually,
This
like
week.
this Monday on the 30th, September 30th.
Mm.
Yesterday, yeah, yesterday was the first day of the quarter. Yeah.
I don't know. When I first joined microbiology, I literally just like, all right, no more fooling around. And then now I'm just like, oh my god, just let the quarter end.
Yeah, yeah. Now you just want to pass. You just want to get it through, get it done, huh?
Yeah.
Dang, it's tough. It's tough. But
Yeah.
what you have finals December though, right? Like you have October and November to bring it up.
It's a quarter system, so basically it just like the quarter ends like next we got this week and next week is finals. So like it ends next week.
Uh-huh.
So yeah. And then a new quarter starts the week after next week.
Hmm. I see. Dang. Oh yeah. So we should like study together. Like you know how we did that one day, that one morning that I think I just went to sleep.
You
I
just
gave
want to
up.
see, yeah.
I backed out. How'd you do that
I
day?
knocked out like for like the past 2 weeks, no, like
Uh-huh.
3 weeks. I just kept like knocking out on my bed when I was like assignment due.
I
It's just like
know.
I missed like one thing like every like for one class, but like it wasn't for every class. But it was just like it became apparent to me that it was unmanageable.
Yeah, yeah. It is.
I was just like, oh shoot, it's like 2 in the morning. I just lie in my bed or like any surface whatsoever, and then and then it's over, and then it's just like warning.
I
It's
know, and
like
it's gonna get like tougher throughout the year, like this year, because like it's becoming winter, and then it's gonna be like so cold outside, so dark outside. Like it's gonna be very sleepy, you know.
yeah. Hmm. I- oh yeah, you want to hear some good news?
Yeah, let's hear it.
Uh, so I got my driver's license already, but
Oh,
they sent in the card
uh-huh,
like for the driver's license, and now it expires like 4 years from now.
uh-huh. That's
Yeah.
good. Let's go.
Yep.
So have you been driving to school and around lately?
I don't have insurance, so I can't like because it's California and I don't have insurance, so yeah.
Uh-huh. Dang. Dang. Excited for you. And how old are you now? Like
16
oh yeah, yeah. So like you got it like the earliest you can legally.
legally. Yep.
That's good. That's so good. I think I also got my license, provisional license, when I was 16, but I started driving like you when like 15, like with the permit. But someone had to supervise it.
Mm.
Um, yeah. So it's pretty fun. Like you get to go anywhere you want. Uh, drive. Like it's kind of therapeutic. Like driving around, listening to music, podcasts. It's really relaxing.
Mm-hmm. for the for this quarter, like basically what's happening is just like I could like leave one class on like a back burner and like not have to worry about it, and I'd still have to get an A. I just it's an easy A. But now it's just like every class right now is just like I gotta like make it like at least like 5 points higher, like 5 percentage points higher, just so I can get like a B in
Uh-huh.
like every single one of them.
Dang. Do you have a plan to do that, or like is it
Plan?
feasible?
No, I'm thinking about it right now. It's just like because like this is probably my only like free day where I get to like think about stuff and like I don't know, I have a little bit of notes to do, but it's just mostly like planning now. Just like, oh my God, how am I gonna do that?
I know it's like pretty stressful, huh? Like, so you want to get a good grade for it
Yeah.
too. Yeah, I remember. Shoot. Well, what I added in the school calendar, if you check, is like every Sunday, 9 to 10 p.m. Like we could just talk and like no OChem, like no chemistry stuff. Like we just talk, catch up, maybe study, like chill, relax. Yeah, you know.
Wait, was that like last week also?
No, no, no. The first one is gonna be the Sunday, the
Oh,
very first
good,
one.
because
Yeah.
I thought I missed it.
No, 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 no. I want you to be there for the first one because you're an OG here. There's been a lot of people like joining this community, um, but they haven't been going to the office hours because like you know how I tutor organic chemistry or like I'm picking up Gen Chem and Biochem right now. Like so like we couldn't talk that much, but that's why
Mhm,
I added this thing on Sunday where we just talk without any chemistry stuff for you.
mhm.
Tutoring. Yeah. So yeah, if you can make it, then that would be great.
Yep. Okay, so the exact date where we first met was like May, like May. So like, let's see.
Yeah, like it was like May something, May
May
14th,
May
15th,
15th, May
May
15th.
15th. Yeah, yeah. Dang, that's like almost 5 months ago. Like 2 more weeks in it, it would be five months ago.
Yeah, that's true.
Yeah,
Uh,
I'll try to like tell the other people about this session on Sunday too. Where there's no chemistry talk. So then we could talk to like different people as well. But if not, then it could just be me and you as well.
yeah, the OG.
Uh-huh. The OG member.
My brain is not working properly, but I'm trying to use it to like think of words. So like to say, just give me a minute.
Uh-huh.
So I don't know. So like recently, I've been like since I'm like hella tired, I've kind of just been like doom scrolling whenever like I don't really have stuff to do. But it's kind of bad because like when like the timer goes off and I have to do something, I kind of don't. So I have like two things that I do. Just like one, I count the amount of like either reels or like videos I've watched, and if it goes above a certain amount, I just stop. And then like also have a second computer, so I like keep a timer there. Just like oh like Pomodoro, and then like
Yeah.
short break, long break, and then that's it. Like,
Uh-huh.
yeah, I think it'll work for like at least 2 weeks, and then I'll probably get sick of it and not use it again. But I just need 2 weeks
Uh-huh.
to like focus.
To focus, right.
Yeah,
And how's that like how's it like have you been experimenting with different things to try to focus? Like what's been working for you and what's
not
not
coffee.
for you?
Coffee, I still black and just knock out still.
Uh-huh.
Yeah,
Dang,
does not work.
dang.
Also, I've been like sleeping with the lights on, just like I'll just take a little nap, and then when I wake up, all the lights will be on, and I'll still be awake. It's like no, I just knock out, and then the lights are still on, and sometimes it bugs me, and I just wake up like 30 minutes after, but I
Uh-huh.
have no energy to get up. So basically, it's just I wake up, I see the light, and then I just close my eyes, and I keep dreaming, and basically I just have like consecutive dreaming like patterns of just 30 minutes.
Oh my god, yeah. I think I've been through that too. Like that happens to me too. Like I'm so lazy to like go close the eyes and I just like sleep, take a nap, and then like go in like cycles of sleeps.
Yeah, deep
Crazy.
sleep, light sleep, deep sleep, light sleep.
Yeah, I know.
Yeah.
Have you been doing the push up challenge thing?
Uh, no, I can't bring myself to do that right now.
Yeah, you gotta focus on your classes. Like that's your priority right now.
Uh-huh. Mm.
What's the averages been like for the classes, the exams that you had?
Averages,
Uh-huh.
like I usually score like 70 just because like and also my brain is just kind of fried already.
Uh-huh.
Yeah. Like 70 is the average, but now it's just I don't know. It's like right now. Okay, I'll just see. Let's see.
Hmm.
Um okay, found it. So 79, 73 is microbiology honors. AP Lang, AP language is 978, and US history is 88.
Oh, okay.
Yeah, so an honors and AP class get an extra 8 boost. So
Mhm. Yeah,
yeah.
it's pretty good.
I mean it's just for weighted, not unweighted, but still I just need it to go up like 2% and then I'll be chill.
Huh.
Hmm.
Mhm.
Oh yeah, I haven't told you this already, but I've joined water polo.
Oh, you joined water polo? Oh my God. How's that going? Like for you right now?
Uh, I mean, I need to like probably get more clothes because like, but also I'm currently learning how to swim, and everyone else is just already in the water with like me, and like practice already started like a month ago, I think, and I don't know, it's just my classes and everyone else, and I guess no one else is in biotech besides this one other person. But yeah,
So has that been taking up a lot of your studying time
not
while
a
in
lot of
Belgium?
time. It's mostly just like I have to sit down and like I get distracted easily, so I'm trying to find a way out of like not getting distracted. So
Not getting
basically, what's also funny is that I feel like I've been doing worse when I don't take care of myself,
mm,
and then or just like neglect sleep and eating, and then
right.
before I didn't like it wasn't my grades weren't this bad when I did like take care of my health and then eating habits before, and then I would like get a normal grade.
Right.
Yeah, I had to learn the hard way. Just like, I'll save more time if I don't eat breakfast or lunch, and I'll just come back at like 6 p.m. to eat dinner and something like that. I was like, oh no 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 no.
I know, yeah. Do you want to have a study session this Sunday, like before um the talking session at nighttime? Like if you're free, like we could study. Like I need to like study for my classes, catch up on
That's what
reading.
I'm planning on doing.
Uh-huh.
Cause like on the weekends, it's just like I'm free, and then I kind of just like I start relapsing on like the reels, and just like
Yeah, we gotta keep each other accountable, Ryan. We gotta like do the Pomodoro technique thing again.
yeah.
So let's set up a time on Sunday to study. And like, how long do you want to study for?
I feel like I don't know. It's just me, but like shorter, like not longer breaks, but like
Uh-huh.
shorter studying sessions, and not like the 1 hour. Wait, no, actually the 50. Let's do like 45, 15 probably.
Okay, 45, 15.
Because last time it was like 50, 10. And it's like, Ryan, I can't do this. I gotta go to sleep.
Yeah, I know. That was so bad. I was so sleepy that time. I felt so bad.
Yeah. 45, 15 sounds good.
Uh-huh. Okay, 45, 15 sounds good. Um, what time works best for you so that I could put this.
So also I'm involved in a club where I have
Uh-huh.
to wake up early, like at like 7, so I can go to school like 7:15. It's
Uh-huh.
break dancing club.
Oh,
And they my school hired like a break dancing not teacher or
uh-huh.
so, and basically you just like gonna teach us how to break dance, and it's just
Yeah.
like for like a multicultural event or something like that.
Dang. Well, dang. So you've been joining a lot of clubs, huh? Like water
No, just like
polo.
it's mostly sports and then like one club that I like, but yeah.
I see. Dang, that's good. Yeah.
Also, if I'm not there, you can also check out this other website called like Life at. It's basically like it's basically like a studying website where you just like
Uh-huh.
you could either like not study with other people, but it's like ambience basically.
Oh, lifeat.io.
Yep.
Okay, okay. Oh
Actually,
shoot.
not
You know all
IO,
the
not IO. It's like more like Life at Spaces or something like that. Because like you gotta pay for you gotta go for an account, but I just usually use the free version of Life
mm,
at.
I see. Dang. Oh yeah, yeah. Okay, okay. Yeah, we'll figure out a time through Discord. Like probably after lunch or something.
Yeah,
Uh,
lunch after lunch, so we can both eat and not just fall asleep right after.
yeah. Uh-huh. Or should we take like a power nap after lunch and then get straight to it?
True, true.
Yeah. So then we can have that good focus.
The energy.
Yeah. Because I don't want us to be both tired right after lunch. You know, like I want us to like feel rested after
hmm
lunch, and then we get into the study session. Yeah.
Yep.
Hmm.
All right.
Yeah. So I
Mm,
will see you tomorrow office hours if you can, and this Sunday as well for the study session and
mm,
the yapping session.
Yep.
Yeah. Okay. Yeah. Good
All
night,
right.
Ryan.
That sounds good. I'm a plan it right now.
Uh-huh. That's good.
All
That's
right.
good.
Lock in, guys.
Yeah. Let's lock in.
Yeah.
Yeah. Okay. Yeah. Good night, Ryan.
Good night, Brian.
See ya.